Hello again, and welcome to the fourth part of this multi-series of videos explaining essentially chapter 13 from the Moran reference book for thermodynamics. And in this part, we will be looking at what's called heating values. Now, what is a heating value? Heating value, or the calorific value, is essentially the energy change, or rather the difference between the enthalpy of the reactants, as you can see, and the enthalpy of the product. Okay, so it is essentially the amount of heat energy that is being released. So the delta H as you go from the reactants to the products, right? And this is important to us because this is what we use to generate work, right? And now, well, this is the main formula that you can think of when you're thinking about heating value per mole of a fuel. So these would be the these would be the enthalpy values per mole ratio for the reactants, and these would be for the products, right? And you essentially sum them up for every reactant and every product, and then you get the difference. Now, there are two different types of heating values. There's the higher heating value and the lower heating value. Now, I want you to recall for the combustion of hydrocarbons, you have hydrogen reacting with oxygen to form water, right? So it will form water. Now, in the standard state, water is a liquid. So in the previous video, I mentioned what's called a standard reference state or the standard conditions. Under those conditions, water is a liquid. So if you have the combustion reaction taking place such that water is in its standard state, then what happens is that you will get the higher heating value. However, if water is not in its standard state, if it is instead released in the form of water vapor, so in the gaseous state, you will get the lower heating value. Another way you can think of it is that the higher heating value and the lower heating value, the difference between them is just the difference in energy between the water vapor and the liquid water. So the amount of energy it takes, or is released rather, the amount of energy that is released as this gaseous water condensates and forms liquid water. Okay, this difference is exactly the difference between these two values, this higher heating value and this lower heating value. And this is essentially what they've said in this part. Now you've got, again, your table 825, and it's a very useful table because it lists all the heating values, not only the higher heating value, but also the lower heating value for a bunch of combustible, essentially a bunch of combustible reactants. And now we're looking at another example of a problem. It's a simple problem. And essentially, they've asked us to evaluate the lower heating value of a liquid where all the water vapor is assumed to be a vapor. So when all of it is vapor, it is obvious to us that the energy change for this reaction will be equal to the lower heating value. So you do the calculations, I mean, in the same exact way that we did the previous example. And since it is in standard state, everything is in the standard state before the reaction. Well, we can just do a bunch of calculations here because, again, the delta H should all be 0. And then you're just left with the formation enthalpies. And then the formation enthalpies for the elements will also be 0. So again, you get a bunch of other cancellations here. And now you're left with the formation enthalpy of octane, formation enthalpy of oxygen, carbon dioxide, and water. And then you can look them up again in your table 825, put them in according to their respective molar proportions. And from there, you can then get your lower heating value. And here they've actually done an extra step where they've actually divided out by the mass of what seems to be the octane, because the original question was evaluate the lower heating value of octane at and compare. Well, let's see. Well, in this case, we're getting the specific enthalpy. So we have to divide out by the mass of whatever is reacting, in this case, octane, right? So you get the lower heating value, and this is based off our calculation, and this is the more accurate value that we get from the table. As you can see, the difference is extremely small. And actually, the difference is just one in this case. Now, the next part is the adiabatic flame temperature. Now, previously, we looked at the idea of a theoretical amount of air and complete combustion. So when you have the theoretical amount of air, right, and you have complete combustion, and you have no heat transfer, which means as this process across this control volume approaches an adiabatic state such that there is no heat transfer, and you have all three of these conditions, the temperature of the combustion products by the end of this control volume will be what we call the adiabatic flame temperature. And in fact, it will be the T max that these combustion products can reach. So this will be at the maximum temperature. So again, because in the absence of work done across this control volume, the drop in temperature will be lower and lower and lower until it's zero when the work done across the control volume is zero, and as well as the heat transfer. So when you have no heat transfer, you have none of this work done, you get all the energy from the combustion being transferred to the combustion products and the temperature being raised to the maximum value. And this maximum value is what we call the adiabatic flame temperature. All right. Now, again, they've basically said the same thing here. So the maximum adiabatic flame temperature corresponds to complete combustion with a theoretical amount of air. So the actual adiabatic flame temperature is just the temperature that would be achieved in the limit of the adiabatic operation. So no matter the amount of air, well, I seem to have made a mistake here. The actual adiabatic flame temperature is just the temperature of the combustion product as the process is adiabatic. So as you remove this work and as you remove this heat transfer, right? However, the maximum adiabatic flame temperature can only be achieved when you have the theoretical amount of air. So the minimum amount of air that you need for complete combustion. And here is an example where they've told us to basically plot the adiabatic flame temperature for X, where X happens to be the, well, excess of theoretical air, right? And so we can set up the equations, and then we can run a computer simulation, and we can get this graph. And as you can see, at the theoretical, when X equals 1, or when the amount of air is the theoretical air, you will get the maximum adiabatic temperature. Now, I seem to be done with this particular part, so I will end it here, and thank you for watching.